Okay, Chapter 11, Section 9, Representations of Functions as Power Series. Okay, in order to do well in this section, and really the next couple of sections, you really have to get very, very comfortable with geometric series. So let's revisit those really quickly. So this was from Chapter 11. Back in Chapter 11, Section 2, we first visited geometric series. So to refresh your memory, a geometric series is one that fits this form. We have this infinite sum as n goes from 1 to infinity of some constant and then times some common ratio r to the power of n minus 1. Right? If we were to expand this out, we would have some constant a, and then when we replace n with a 1, we end up with r to the power of 0. Right? I'll just go ahead and put it in r to the power of blank minus 1. And then that blank is going to be this 1. And then the next term is going to be plus a r to the blank minus 1. And now the next term is going to be a 2 plus a r blank minus 1, and then this is the third term, plus dot 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 dot. This goes on forever, right? So we can simplify this a little bit more. This is just going to become r to the 0 power, which is just going to be 1. So then we end up with the first term is just a plus, and then 2 minus 1 is 1, so this becomes ar to the power of 1 plus ar squared plus, and now we see the pattern, ar cubed, and so on and so forth, so on and so forth. Right? So the terms are almost identical. They all have a constant a, and then they all have a power of r to a power of something. And if we really want to complete this pattern, we can, sometimes you see this written as times r to the 0 power. That way we see 0, 1, 2, 3, and so on and so forth. But I think most commonly you don't see that in there. Okay, and so the terms are almost identical, except they gain a power of r from one term to the next. There's one more extra factor of r. So we say the common ratio is r. Right? From one term to the next, we just have an extra power of r every time. So we say that we have a common ratio of r. Okay, so we learned all about this in Chapter 11, Section 2. If you forgot some of this stuff, you should go revisit at least just this part of it. Like I said, we're really going to need it, and we need to know it well for this next section. Okay, so upon further investigation back in Chapter 11, Section 2, we saw that we can find out when this thing converges. And so we discovered that it converges whenever the absolute value of r is less than 1. So this to infinity a r to the n minus 1 converges for the absolute value of r being strictly less than 1. And not only that, this is one of those rare cases where we not only know that it converges, we also know what it converges to. We saw that the sum of this geometric series is equal to the following. This is ar to the n minus 1, and goes from 1 to infinity, that this sum is equal to a over 1 minus r. Right? Again, assuming that it converges. So this is, again, for the absolute value of r being strictly less than 1. So as long as the common ratio is equal to some value strictly less than 1, then we know it converges, and we know what it converges to. Right? Let's explore that real quick then. So for example, Let's say I had the sum 3 times pi over 4 to the power of n minus 1 as n goes from 1 to infinity. Okay, so this is going to end up being the infinite sum of 3 for the first term, right? So we put an n equals to 1 there, we get a 0. So the first term is just going to be 3. The next term is going to be 3 times pi over 4 to the power of 1. That's the second term. Plus 3 times pi over 4 to the power of 2. Plus 3 times pi over 4 to the power of 3. Dot, 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 forever. That infinite sum that goes on forever is really going to be equal to this because it converges, right? So here R equals to pi over 4. And the absolute value of pi over 4, well, it's positive already, so we don't really have to put an absolute value, but this is definitely less than 1. So because that's true, pi over 4 is less than 1. For that reason, we can conclude that not only can we conclude that this part converges, that the sum will exist, pi over 4 to the power of n minus 1 converges, but we can actually know what it converges to, right? So this infinite sum, 1 to infinity, of 3 pi over 4 to the n minus 1 power, this infinite sum is going to be equal to a, where in this case a is equal to 3, all over 1 minus r, which is pi over 4. Right? Whatever this is whatever this infinite sum is going to add up to. Okay, so now we take our calculator and we can just punch this guy in. So I would start with pi divided by 2, pi divided by 4, sorry, enter, and then 1 minus that guy, enter, gives me that decimal, and then finally 3 divided by that decimal gets me to that one. Okay, so it's approximately 13.9794, 13.9794. 13.9794, approximately. So I shouldn't put an equal sign there. Let me just erase this guy. It's an approximation. Okay, so what are we saying? We're saying that this whole thing right here is approximately equal to this decimal, right? Going out to infinity, the summation, the infinite sum of all those values, all those terms with a pi over 4 raised to different powers out to infinity, the whole thing just adds up to about 13.9794, right? I think that's pretty interesting. Okay, so that was the geometric series back from 11.2. All right, well, more recently, we looked at the power series from chapter 11. In chapter 11, section 8, we looked at power series. And a power series was something that fit this form. N goes from 0 to infinity of c sub n x minus a to the power of n. And, well, okay, let's just expand on this a little bit. The first term is going to be c sub naught, x minus a to the power of 0, plus c sub 1, x minus a to the power of 1, c sub 2, x minus a to the power of 2, and so on and so forth, right? And this goes on forever. Okay, one type of power series that we looked at was this one. We said, well, what about just the more simple one kind of flew under the radar. We just kind of covered it for a little bit, and then I didn't really mention it very much. This simple looking one, this one is also a power series. This is a power series. Right? This is a power series with the constant c sub n just equal to 1, right? If we made all of these constants here just equal to 1, I shouldn't say constants, coefficients, all these coefficients here just equal to 1, then we get this guy. And then also the a is 0, and a equals to 0. Right? So if we expanded this guy, we get this goes from 0, x to the n. Okay, the first term is x to the 0 plus x to the first plus x to the second plus x to the third. Oops. X to the third plus x to the fourth plus so on and so forth forever, right? This goes on forever. And that first term, x to the 0, is just going to be a 1. So this is 1 plus x squared plus x to the third plus x to the fourth plus dot forever. Okay, well this looks very familiar. This is in fact a geometric series, right? And then the common ratio from one term to the next, right? All the terms are identical except to get from one term to the next, that common ratio is just x this time. So this is a geometric series with the common ratio of x. The common ratio of x, right? And the constant a is now equal to 1, right? So from right above here, this is what a geometric series looked like. It started from 1 to infinity of some constant, and then some common ratio r to the power of n minus 1. And when we expanded this, we got a plus ar plus ar squared plus ar cubed plus dot. Okay, well this is equal to that, except it's got the a value is 1, and then instead of an r, the r is an x. X is our r. It is our common ratio. Right? So that's what we want to conclude here. This is a geometric series. This is a geometric series with r equal to x, that's the common ratio, and a equal to 1. Okay, well, since it is a geometric series, we know that it will converge as long as the absolute value of r is less than 1. So in our case, that's going to be when absolute value of x is less than 1. Right? So that's what we can conclude out of this power series. From 0 to infinity of x to the nth power will converge for the absolute value of x being less than 1. Okay, well, the absolute value of x less than 1, another way of saying that is that it'll converge for x being a number trapped between -1 and +1. It's another way of saying the exact same thing. You can also say the exact same thing by putting the interval. It will converge on the interval from -1 to +1, and we don't want to include the endpoint, so we put parentheses. Okay. Or if you really want to come up with another way of doing it, we can also graph it, right? So we can look at the number line, look at x, the x-axis, and then let's say this is 1, so we go out here to +1, we go back here to -1, and so we would say that everything in there, whenever x is a value trapped between, oops, this is a 0, not a 1. Here is 0, and so we go out to +1, over here to -1, and every value in there, as long as you choose a value of x somewhere in there to plug into this power series, it will converge. Right? So we also say that this is the interval of convergence. Okay, so this is a very powerful statement here. Let's just do an example just to make sure that this is sinking in. We know that, for example, if x equals to pi over 4, then what's happening here? We have the infinite sum as n goes from 0 to infinity of pi over 4 to the power of n. And so if we expand that out, the first term is just going to be 1. The next term is going to be pi over 4. Next term after that is just going to be pi over 4 squared. The next term after that is going to be pi over 4 to the power of 3, and so on and so forth, and so on and so forth, like that. And so we're saying that this thing is going to converge because will converge because the absolute value of pi over 4 is definitely less than 1, so it converges. Not only does it converge, but we know what it converges to. We know the sum of this thing. It's going to be equal to 1 over 1 minus x, and in this case, the x is this pi over 4. Okay, so this is the sum of the entire thing. This is going to be equal to 4 minus pi over 4. Common denominator is 4 over 4, so it's going to be 4 minus pi divided by 4. And then we can flip that upside down and say that this is really equal to 4 divided by 4 minus pi. Whatever that is, that's going to be the sum of this infinite series, this power series evaluated x equals to pi over 4, gives you that sum right there. Okay, so that's what this was trying to tell us. So let's put it together. Let me rewrite this thing one more time, since that's really the key to this whole section. We have that this power series, x to the n, right? And then if we expand this whole thing out, it'll be 1 plus x squared plus x cubed plus dot 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 forever, right? This infinite sum, that it would be equal to 1 over 1 minus x, provided that for the absolute value of x being less than 1. As long as that's satisfied, then these three statements are true, right? This is really the key to this whole section. This is equal to this, which is equal to that. All three pieces are equal to each other. And so usually we see it in this direction, but really we just want to flip this around. So we can kind of flip the tables on this a little bit and say, well, then that means that this is also equal to this, 1 plus x squared plus x cubed plus dot 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 dot. And so this whole thing is then equal to this power series of n0 to the infinity x to the n. Right? Again, provided that this is for the absolute value of x is less than 1. Right? That's important to keep that in there. That's the condition that allows this to happen. Right? If the absolute value of x is greater than 1, then we know that this series diverges, and so this is no longer the sum. Okay, well then this allows us to play around a little bit. We can move things around and change things a little bit. So let's do that a little bit. So for example, we could say that we could have 1 over 1 minus, leave that as a blank, and then 1 plus blank, and then blank squared plus blank cubed plus dot 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 forever. And then that's going to be equal to the sum as n goes from 0 to infinity of blank to the nth power, and this is for blank, and absolute values is less than 1. Okay, so Obviously, I could just stick the x back in there, and we would have exactly the one above. No changes whatsoever. Okay. Or we could change the variable. I mean, there really isn't anything inherently special about x. So who's to say it's not a y in here? 1 over 1 minus y could be expressed as 1 plus y squared plus y cubed, dot, 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 dot. So there's a y in there. And then that's only going to be true as long as the y is less than 1, right? Nothing different about that. Okay, well, we can also change it a little bit in a different direction. We could rewrite this as, for example, a 2x instead of just an x, which would mean that there would be a 2x in here, a 2x in there, a 2x in there, dot, 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 which means that this guy would be 2x to the power of n. And then this would be good as long as the absolute value of 2x is less than 1. Good, 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 good. Okay, again, we can just keep playing around with this a little bit more. Instead of a 2x here, we could change that and make it be how about we can make it a negative x squared. Okay. And so now that means that this guy must be a negative x squared, which means that this must be a negative x squared, means that this must be a negative x squared, dot, 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 which means that this must be a negative x squared, which means that this must be a negative x squared. Okay, so we can play around with this, manipulate it a little bit, and we're able to rewrite some of these statements here as a power series, right? That's the whole point of this thing. Why would you want such madness? Well, we'll get to that in a second. But let's look at another example. So on your homework, for example, let's look at some of your homework problems. Okay, so let's take a look at some of the homework problems. We're already able to answer the first few of these. So say something like these guys. Find a power series representation for the function and determine the interval of convergence. Okay, so let's take a look at, say, for example, number 4. F of x equals to 5 over 1 minus 4x squared. Okay, so question number 4 in section 9, chapter 11. Has this function. Okay, and so this looks an awful lot like the result of the sum of a geometric series, right? So what we want to do is note that this can be rewritten as 5 times 1 over 1 minus, and then put this guy like this. And so this is equivalent, or it's similar to the idea of having this, right, which we just covered. And this thing is a geometric series, and its sum is going to be equal to this x to the power of n, this 0 to infinity, right? It's a power series, it's a geometric series, right? It's both, and it looks like this. Good. So this guy then is equivalent to 5 times the sum as n goes from 0 to infinity of blank to the power of n, and that blank is this. So it'll be 4x to the power of 2. Okay, so now we just have to simplify this a little bit. We get a 5 times the sum as n goes from 0 to infinity, and then this just simplifies to what is that, 2 squared, so we can say it's 2 squared times x squared, the power of n. So we can pull that out and say that this is 5 sum n goes from 0 to infinity of 2x the power of 2n. That's one way to put it. Or we can separate it and put 2 to the n x to 2 to the 2n times x to the 2n. Either one is fine, but I think this one works. And then when does this converge? Well, it will converge back up here whenever this thing was less than 1. Right? This is 4. This absolute value of 4x squared is less than 1. Good. So we can pull out that 4. That's not doing anything. 4 absolute value of x squared is less than 1. Well, the squared isn't going to do anything. Any value of x once you square it is going to turn into a positive, so the absolute value is not impacting that. So we can say that this must be true. And so x squared less than 1/4. And so this is going to be true as long as we have that the absolute value of x is within half, right? If we take the square root of both sides, then we'd have to think about the plus and minus, right? So in other words, this has to be a value trapped between negative 1/2 and positive 1/2. Right? As long as we have some value trapped between negative 1/2 and positive 1/2, once we square it, we're still going to have a value that's less than 1/4. Okay. All right. Well, another way of saying the exact same thing is saying that it's going to converge as long as we have a value of x in the interval between negative 1/2 and positive 1/2. Okay, so this is the power series representation, kind of putting it all together. We have that f of x equal to 5 over 1 minus 4x squared. This function has a power series representation equivalent to this, 5 times the sum as n goes from 0 to infinity of 2x to the power of 2n. So this is its power series representation. And this will converge for x being between negative 1/2 and positive 1/2. Also, note that the radius of convergence r is equal to 1/2, and that this is a power series centered at 0. So we'd say that this is a power series centered at 0. Okay, then interval convergence there, right? Okay. Another way that this might be presented might just be something like this: 5 sum 0 to infinity. I think this is how I saw the author do it. This is just going to be 4 to the nth power x to the 2n power. So either one, either that one or this one, same thing. This is where it converges, interval of convergence, radius of convergence is 1/2, it's centered at 0. Okay, not bad, right? And again, this was really just playing around with this again. Well, I was just over here, right? All I did was replace this. All I did is replace this thing with a 4x squared, 4x squared. So each of these terms go 4x squared, 4x squared, 4x squared, dot, 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 dot. And so we end up with a 4x squared. And so that's why it has to be true that this must be 4x squared as well. And then there was also this other constant that was like a 5 up here. So we just have to throw in that there's also a times 5 out there. Therefore, there's a times 5 there. And there we go. That's all I did for that problem. Okay, all right, let's try one more. How about number 8? X over 2x squared plus 1. And so we have that f of x is equal to x over 2x squared plus 1. Okay, so I'm going to manipulate this a little bit. I'm going to, first of all, move out this x. 1 over, and then just flip those around, 1 plus 2x squared. And so now it's starting to look a lot like what we need, times 1 over 1 minus negative 2x squared. Good. And so now that fits the form I want. This is going to be equivalent to x times, and now this part right in here is the sum as n goes from 0 to infinity of negative 2x squared to the power of n. And this will converge as long as this part is within 1. So converges for the case where the absolute value of negative 2x squared in absolute values is less than 1. So we'll deal with that in a second. This guy we want to simplify a little bit more. This turns into sum as n goes from 0 to infinity. When we distribute these, we end up with negative 2. Well, let's separate those two as well. Okay, never mind. We'll end up with negative 1 to the power of n, so I know it's going to be alternating. And then I'll have a 2 to the power of n. And then there's this x to the power of 2n. And then I can bring that into there and combine them. And so this is going to become x goes from 0 to infinity, negative 1 to the power of n times 2 to the nth power times x to the 2n plus 1 power. Right? And this will converge as long as this is true. So let's simplify that as much as we can. The absolute value is not going to affect either one of these things. So, well, it's not going to affect the x squared. It will affect that. So we'll change that into just positive 2. X squared has to be less than 1. And so x squared has to be less than a half. And when I do the square roots, it must be true that the absolute value of x is less than 1/4. Oops, not 1/4. 1 over the root square root of 2. 1 over root 2, which means that x must be a value trapped between negative 1 over root 2 less than x less than 1 over positive root 2. Good. Or another way of saying that is it's got to be on the interval between negative 1 over root 2 comma positive 1 over root 2. Good. So again, this is a power series centered at 0. So this is a power series centered at 0 with radius of convergence capital R equal to 1 over root 2. Good. And this is the interval of convergence. Interval of convergence. Okay, so what did we do? We took an innocent little function, kind of bringing it all together. We took this innocent little function. F of x is equal to, so this was number 4. On number 4, we took this innocent little function, f of x equals to 5 over 1 minus 4x squared, and then we turned it into this this power series at n goes from 0 to infinity. Wait, that was, yeah. So we took this nice little function and we set it equal to that power series for number 4. And then for this one on number 8, we took this other innocent looking function of x over 2x plus 1, 2x squared plus 1. And again, we turned it into this ugly looking power series. 0 to infinity of, and what was it? It was this one, negative 1 to the power of n times 2 to the n power times x to the 2n plus 1. Very, very ugly. And of course, this is only valid over a certain domain, so this is 4. And we established that for this one, it was for negative 1/2. This was for negative 1/2 to positive 1/2. And for this one, it was for x being somewhere between negative 1 over root 2 to positive 1 over root 2. Okay, so we did it. We got the answers. We were able to convert this innocent-looking function into a power series representation of that function. We could do it, but you might be wondering, well, why would we want to? What's the point of this? What's the benefit? What's the advantage of doing this? All right, let's do one more example. Let's say we are given f of x equals to, let's make it really ugly. Let's make it x to the 5th power all over x plus 3. Okay, so what are we going to do with this guy? I'm going to manipulate it a little bit. I'm going to pull out that x to the 5th and separate it from the 1 over x plus 3. And then I'm going to switch these around. That becomes x to the 5th times 1 over 3 plus x. So I'm getting a little closer to that 1 over 1 minus x. Okay, so here I'm going to manipulate this a little bit by multiplying through here a term of, I need to get rid of this 3, right? So I'm going to multiply x to the 5th power times 1 over 3 plus x. I'm going to multiply through here a 1/3. 1/3. That's going to give me a 1/3 plus x over 3. I can't just go around multiplying 1/3 everywhere, so I have to also multiply the numerator, denominator. Okay, well, that means that this f of x function is equal to, well, we can just pull out that 1/3. 1/3 x to the 5th power times 1 over, and then this becomes 1 plus x over 3. Almost there, we just need this to be a minus. So this becomes 1/3 x to the 5th power times 1 over 1 minus, and then here we'll end up with minus x over 3. Okay, finally, that looks exactly like what I need. And so this will be equal to 1/3 x to the 5th times this sum from 0 to infinity of, and then it will be this term raised to the nth power. Okay, and this is valid as long as this is less than 1. So converges for the absolute value of negative x over 3 being less than 1. Okay, so that means that the absolute value of negative x has to be less than 3. Which means that x must be a value. Which means absolute value of x must be less than 3, or x must be a value between negative 3 and positive 3. Okay, and now this guy we can simplify a little bit. This is going to be something that's alternating. It's going to be 1/3 x to the 5th power, and then 0 to infinity, and then we'll have a term that's alternating to the nth power, and then x to the nth power all over 3 to the nth power. And now we can bring these guys in. So this is going to be the sum as n goes from 0 to infinity of a term that's alternating, x to the nth, and then we'll have an x to the n plus 5, and then this whole thing gets divided by 3 to the n plus 1, right? And again, this is 4, it'll converge on -3 to +3. Okay, now let's pause and think about what we've done, right? Let's kind of step back and take a global picture because it's so easy, I think, to get lost in the middle of this whole thing. Okay, so let's step back. What did we do? Where did we start? We started off with this simple little function over here. F of x equals to x to the 5th power all over x plus 3. And then we went through this very challenging transformation that ultimately led to this, right? So what we've done is we found a power series representation of this function. This function equals to this power series representation. So let me write that down here. So we have that f of x is equal to x to the 5th power divided by x plus 3. And we also have that this is, in fact, actually equal to exactly that power series representation, the infinite sum, 0 to infinity, of this crazy thing, -1 to the nth power, x to the n plus 5 power, all over 3 to the n plus 1 power. And this is 4, right, when it converges. This is for x values, for x between, well, let's use this notation of an element of, for x being a member of or an element of this section from -3 to +3, okay? And in fact that this, if we expanded it out and we started building out the terms, when n equals to 0, we end up with positive x to the 5th over x to the 3rd. Plus, when n equals to 1, we end up with negative, we end up with a minus x to the 6th over 3 to the 2nd power. Plus, okay, and then we can see that the pattern is pretty easy. I'm going to go out a few terms here. 3 to the 3rd power minus x to the 8th power, 3 to the 4th, plus x to the 9th power, 3 to the 5th, minus x to the 10th power, 3 to the 6th power, plus x to the 11th power, over 3 to the 7th power, minus dot, 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 dot. Okay, the pattern continues from there, right? So we have the first 1, 2, 3, 4, 5, 6, the first 7 terms, and then it goes on forever, right? So in its entirety, if you go out to infinity, then that whole infinite sum is equivalent to this, right? They all represent f of x. So in fact, I can write it, just to kind of separate them, I can write that this guy is f of x like this. This is f of x. And then I can say this way, well, okay, also f of x equals to x to the 5th over x plus 3. Or I can write it this way, right? So I can just copy that part. Right, so we're saying that all of these things mean the same. And then, of course, this one and this one are only valid as long as this is true. It must be valid for this one, and then it must be valid for this one. So it comes with a restriction. So this representation of a power series to represent this function is only valid for certain values of x. You're like, well, what happens when x is outside of here? If x is a 5, for example, x equals to 5, this one continues to be valid. Yay. However, this fails. This is not going to give us an equivalent answer when x equals to 5 or anything outside of that domain. But as long as x is a number inside there, all three of these things should give you the same answer approximately. Well, I should say approximately here because we cannot actually add up to infinity, but we can stop somewhere and get a pretty good approximation. In fact, let's do that. So what we're saying is, for example, let's just pick a random number that's in the domain between -3 and 3. Why don't we just pick 1? Makes it nice and easy. So, for example, if I wanted to find the value of f of 1, right? So this is, of course, meaning that x equals to 1. Okay, so I can use any one of these three ways of representing it. I can use this way, and if I put a 1 into there, then that means this whole term is always going to be 1. So f of 1 can be written as this, the sum of 0 to infinity of -1 to the nth power all over 3 to the n plus 1, and then I'd have a times 1 to the power of n plus 5, but that's just always going to be 1. 1 raised to the 5th power, to the 6th power, to the 7th power, it's always 1. So we don't even really need it, and we can just kind of get rid of it and say that's what happens when x equals to 1. It turns into this. Okay, and that's an infinite sum. And we can expand that out a little bit and say, well, f of 1 is also equal to, and then we can kind of use this pattern here to guide us. But again, all those powers, 1 to the power of 5, 1 to the power of 6, 1 to the power of 7, they all just become 1. And so this pattern then just becomes 1/3 minus 1/3 to the 2nd power plus 1/3 to the 3rd power minus 1/3 to the 4th power, right? I'm just replacing all these x values here with a 1. That makes it nice and easy. I very conveniently picked a very easy value to work with. 1/3 to the 5th power minus, right? And then we can just continue on that pattern. And then, of course, we could just use the actual function, f of 1 equals to 1 to the 5th power divided by 1 plus 1, plus 3, which then just gives you 1/4, which is 0.25. Okay, all right, so this is not going to be the summation of the first 1, 2, 3, 4, 5 terms. It's not going to be equal to exactly 0.25, but it'll get kind of close, right? If I go out to infinity, all the way out to infinity, it will be equal to exactly 0.25, right? Because these two things are equal to each other. But of course, in practice, we often don't go out to infinity. What we do in practice often is just to get a good approximation. So we can just approximate it by going out to the first few numbers. So let's make sure we have that approximation. So in order to use my calculator, use an approximation, I'm just going to point out that 3 to the 2nd power, well, that's actually equal to 9. And then 3 to the 3rd power, that's actually equal to 27. This is actually equal to 81. And that this is actually equal to 243. Okay, so let's use our calculator to see how this becomes a pretty good approximation of that. Okay, so we're going to start off with 1/3. So 1 divided by 3. Okay, 0.3333. That's pretty close to 0.25, but not quite there. Next, we subtract a little something. We subtract the 1/9. So that previous value minus 1 divided by 9. And we're going to get something that's a little below it now, 0.22. Okay, so it was a little high for the first term, and now after the first two terms, I'm a little low. Now I'm going to add a little something. I'm going to add a plus 1/27. So the previous answer plus 1 divided by 27. Okay, I'm getting a little closer now. Now it's 0.2592, getting a little closer to 0.25. And that's just with 3 terms. But I am a little bit higher than what it should be, right? It should be 0.25. I have 0.2592. Make this a little bit larger. 0.2592, so close but not quite there. So now the next term is going to be to subtract a little something. Subtract 1 over 81. So the previous answer minus, parentheses, 1 divided by 81. Okay, so now I'm a little low. I'm at 0.2469. And then the next term is going to be to add a little something. Now I'm going to add a 1 over 243. So previous term plus 1 divided by 243. And now I'm a little higher, right? So I keep kind of dancing back and forth. I start off a little higher, then a little lower, a little higher, a little lower. And each time I get a little closer to the real answer, which is 0.25. So, like I said, if we had the luxury of being able to go out 100, eventually this will be exactly 0.25. But even with just 1, 2, 3, 4, 5 terms, I'm already pretty close. So that's a clue of why we bother doing this. This gives us a really good way to come up with an approximation to the function. Okay, well, the next natural question would be, well, then why do you even need an approximation? It was perfectly easy to work with the original function and plug in a 1. Why would anybody want to convert it into a power series expression of the function and then attempt to evaluate that expression by evaluating the first few terms? Well, why would anybody want to do this? Well, the key comes in when we want to take derivatives or integrals. So back to our function. If we wanted to take a derivative of our function, right? So back to the fact that we have our function at f of x equals to x to the 5th power over x plus 3. And we said that this is, in fact, equal to this drawn out, it's equal to this thing, 0 to infinity of, no, actually, no. Let's go back over here. Let's just, okay, let's go back to this guy. X to the 5th is equal to x to the 5th over 3 minus x to the 6th over 3 squared plus x to the 7th over 3 to the 3rd minus x to the 8th over 3 to the 4th plus x to the 9th over 3 to the 5th minus x to the 10th over 3 to the 6th plus x to the 11th over 3 to the 7th, forever, right? Okay, we already established this function equals this infinite sum. Got it. Okay, so this is a power series representation of this function. Okay, what if we wanted to take a derivative? Okay, so the derivative, first derivative of this function is equal to the derivative of this function, x to the 5th over x plus 3, which is equal to the derivative of this whole thing. Okay, so now the derivative on this side, well, we would use our quotient rule. So this is not super easy, but also not that bad. This will end up being low d high, so low derivative of the top, low d high, so that'll be 5x to the 4th minus high d low, x to the 5th derivative of the denominator, that's just going to be a 1, divided by the denominator squared. Okay, so this is that derivative. And then we can simplify that a little bit. Scoot this up. This becomes f prime of x equals to 5x to the 5th power plus 15 plus 15x to the 4th power minus x to the 5th all over x plus 3 squared. And then again, further simplify that by saying that this is approximately equal to, combining this term and that term, we get 4x to the 5th power plus 15x to the 4th power, and the whole thing is divided by x plus 3 squared. Okay, pretty ugly, but doable. Okay, and now on the other hand, though, we have a representation of this function this way, and we know from calculus 1 that if we have a long polynomial, right, turns into a polynomial, and we want to take the derivative, then we have a property that tells us that we can just take the derivative of each one separately and then add them or subtract them all together, right? So the derivative of a sum is equal to the sum of derivatives. So we're just going to take the derivative each one at a time, and each one is actually pretty easy. There is a bit of a hiccup here in that this goes on forever, right? And forever can get tricky. Luckily, we will see that there is work that has already been done. Somebody way smarter than me figured out how to prove that it works out for power series. So we are on solid mathematical ground here that it is allowed. We are going to take the derivatives of each one individually and establish a pattern and let that pattern go on forever, and it will work. That's not something we can just take for granted all the time, but it does work out here. So the derivative of the first one is just going to be equal to, well, we have 5 over 3 x to the power of, and then so the pattern is we bring down the exponent and we subtract 1, so it becomes x to the 4th minus 6, 3 squared, x to the power of 5 plus 7 over 3 to the 3rd power, x to the 6th power, minus 8, 3 to the 4th power, x to the 7th, plus 9, 3 to the 5th power, x to the 8th power, minus 10 over 3 to the 6th power, x to the 9th, and then the pattern continues, plus dot, 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 dot. Okay, let me pause and make sure that looks good. So the powers are all going to have one less, so x to the 5th, 6th, 7th, 8th, 9th, 10th, 11th, so x to the 4, 5, 6, 7, 8, 9, okay? And then we always bring down that the exponent and turn it into a factor here. So that's 5, 6, 7, 8, 9, 10. And then we have powers of 3. 3 to the 1st, 2nd, 3rd, 4th, 5th, 6th. Okay, so that looks good. And so this is another way to represent that derivative, right? This whole thing, we can also go back and express it as a Riemann sum, starting with n equals 2. So we can play around with the n's a little bit. In fact, this should be very, very similar to the one we had before. So let's start off with leaving it alone like this. Now the plus minus, that part stayed the same. So let's leave that alone. And then the denominators stayed the same. We always had a 1/3, powers of 3. So there was a power of 3 component to this thing that was 3 to the power of n plus 1. And now we used to have x to the power of n plus 5 before, but now we're going to have one smaller power, right? We always bring one down. So instead of n plus 5, we're going to have an n plus 4. And then there was an extra component here, and then this is that exponent was brought down. So this turns into an n plus 5. Right? So that's another way of expressing this thing. If we just kind of think about the first few terms, we see that they spell out these guys. See the 0 term, that becomes positive. 0, that's just going to give us a 5. That's that 5 right there. 0 is going to give us a 3 to the power of 1. That's that 3 right there. And then a 0 right there is going to give us a power of 4. So that's that first term. When n equals to 1, we get a negative. Okay, we get a negative. N equals to 1, we get a 6 from there. N equals to 1, we get a 3 squared. And then n equals to 1, we get an x to the 5th power. Okay, so this begins to give us that guy right there. And so what we want to establish is that this derivative is equivalent to either this thing or this thing. Right? So let me write those down. So this derivative could be this one, sure, or it could be this whole thing. Let me copy that. Okay, so our derivative, the first derivative of our function, is either expressed this way, or we can express it this way, or we can express it that way. And just like before, we can evaluate our first derivative at a point as long as it's in the domain. Remember, all of these were for x being a member of, and this was from -3 to 3, right? And that's valid for this one and this one. They require that. So these will only be true as long as x is within that interval of convergence. Okay, so let's, for example, try out a number. Again, let's try a simple one. How about 1 again? So let's see what happens when we evaluate f prime of 1, the derivative of the function, evaluated at 1. Well, we end up with 4 times 1 to the 5th plus 15 times 1 to the 4th power, all over 1 plus 3 to the 2nd power. And so that is equal to 1 to the 5th. That's 1 plus, that's going to be 4. And then this is going to be 19. That's just a 1, that's just a 1. That's just going to be 19 in the numerator divided by f prime of 1 becomes 19 divided by 4 squared, which is going to be 16. 19 divided by 16. Okay. On the other hand, we can also use this guy right here. This will also give me my first derivative. Right? So I'll say or f prime of 1 is also going to be equal to 5/3 1 to the 4th power minus 6 3 to the 2nd to the 5th power plus 7 3 to the 3rd power blank to the 6th power minus 8 3 to the 4th power blank to the 7th plus 9 over 3 to the 5th power blank to the 8th minus 10 over 3 to the 6th power blank to the 9th plus dot 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 dot. Okay, so we're trying to let x equal to 1. So we're going to replace x1 there, x1 there, x1 there, x1 there, x1 there, x1 there. So, of course, all those terms that have a 1 to the power of 4, 5, 6, they all turn into a 1. So this whole thing really simplifies to give me 5/3 minus 6 over, and I'm going to expand out the denominator. 3 squared is 9, plus 7 over 27 minus 8 over 81 plus 9 over 243 minus 10 over, what is that? 729 plus dot, 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 dot. Okay, so here is the result of our derivative. And again, I don't have an exact answer because this would have to go all the way out to infinity, and I don't know what that is, but I can approximate it by going out just a few decimal values. So we see from this representation of our derivative that the answer should be 19 divided by 6. So let's get our calculator out. Let's expand this a little bit. Okay, so 19 divided by 16 is that. So the real derivative should be 1.1875. Okay, so that's the exact answer of our first derivative evaluated at x equals to 1. It should be exactly 1.1875. But we can approximate it as close as we want to by looking at this guy over here. So let's use our calculator to do that. Okay, so we're going to start off with 5 divided by 3. And that turns out to be a little too low, right? This is the real answer. This is the target answer. That one's a little too low with just one term. I'm sorry, that's a little too high, not too low. There's a little too high with just one term. It's supposed to be 1.1875. We're getting 1.6666. Okay, so we're going to subtract a little something. So the previous decimal minus this one becomes minus 6 divided by 9. Oops, let's put it in parentheses, make sure it doesn't do something weird. Minus 6 divided by 9. Enter. Okay, so now I'm a little too low. I went all the way down to 1. Okay, so now I'm going to add the next term plus the previous term plus 7 divided by 27. Okay, now I'm a little too high, 1.2529, but I'm getting closer to it. Right? Okay, so then the previous value, I'm going to go down a little bit, and now I'm at subtracting 8 over 81. Minus 8 divided by 81. Okay, getting really close now. Then next I'm going to add this one, plus previous value plus 9 divided by 243. It's going to be equal to that. And then the last one I'll do, minus, and then this one's going to be 10 divided by 729. We get that. Okay, now we're getting really close, 1.1838. That is my approximation for the value of this derivative with just 6 terms. Just after 6 terms, I'm getting pretty close. So if I really wanted to get very, very, very close, maybe I wouldn't do 6 terms, maybe do 100 terms, 1,000 terms, 10,000 terms. It's something that we can do, especially if we have a calculator or technology to help us with that. And then again, it still doesn't quite answer the question, like why would you want to do it this way if you aren't even getting an exact answer, you're getting an approximation. Well, the point is that I started off with a function that was relatively easy, right? Let's go back up here. We started out with this function, pretty easy function, and then to find its derivative, not that bad. But what if we have a function whose derivative is difficult to find, or in fact maybe impossible to find? We don't know how to get that derivative. So if we have a situation like that where we have a function whose derivative is either impossible or incredibly difficult, we just don't know how to do it. One way that we might be able to get around that is that if we can find a power series representation of that function, then we can take the derivatives piece by piece by piece by piece. Each of those individual little derivatives hopefully would be a lot easier to solve. And then we would have a power series representation of the derivative of the function. And then we can expand that out and get a pretty good approximation of the results, right? The farther out you go, the better your approximation is. So that's the point here. And okay, well, this function happened to be fairly easy to find a derivative of. But what if we wanted to integrate, right? So we had x to the 5th power all over x plus 3. Finding the derivative of this wasn't bad, but what about if I wanted to find the integral? Not so easy, right? So it already gets a little hard. On the other hand, if we again go back to its power series representation of that function, then we'd have to integrate this. Integrate the sum as n goes from 0 to infinity of -1 to the nth power x to the n plus 5 all over 3 to the n plus 1. And so this is that sum, that infinite sum. And so we'd say, okay, we'll integrate this. It was 1/3 x to the 5th minus 1/9 x to the 6th plus 1 over 27 x to the 7th. Okay, we get the point. Minus dot, 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 dx. Oops, forgot the dx over here. So integrating this looks pretty intimidating, but then if we expand this whole thing out, right, this in here is equal to this guy, and so we can expand it, and now we know that, well, okay, what we can do is just integrate each piece one at a time. So this is equal to the integral of just this first part, which is going to be equal to 1/3 x to the 5th dx, minus 1/9 integral of x to the 6th dx, plus 1 over 27 integral of x to the 7th dx, minus dot, 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 right? So we see that we've converted something that looked pretty hard to do into this infinite sum of integrals that are fairly easy to do. So now this one is just going to be 1/3. Remember, the pattern for these polynomials is going to be to have x to the 6th divided by 6. The derivative of this is equal to that one, minus 1/9. And then this is going to be x to the 7th divided by 7 plus 1 over 27 times x to the 8th divided by 8 minus dot, 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 dot. Okay, so we can just find that pattern and we can write it down as a power series representation of the integral of that function. Right? So we start to see the benefit of being able to do it this way. Okay, so that's just sort of the idea of where we're heading with this. So let's take a look at what it would look like in general then. Okay, so we want to say that if the function f of x can be expressed, so if a function f of x can be represented as a power series with radius of convergence r being strictly greater than 0, right? So there's some radius of convergence not equal to 0. Then we could say that f of x looks like this. This function is going to be a power series. So the general form of a power series is this, some coefficient indexed by n, and then there's a term of x minus a to the power of n. So this is a power series centered at a power series. this, if we expand it all out a little bit, we can say, well, okay, it equals to that, or we can also say the function f of x. Well, if you start to expand it out, the first one is c sub naught, and then we end up with x minus a to the power of 0, which is just going to be 1. So that first term is just c sub 0, plus the next term is going to be c sub 1 times x minus a to the power of 1, plus then c sub 2 x minus a to the power of 2, plus c sub 3 x minus a to the power of 3, plus dot, 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 right? Same pattern moving on. Okay, so a theorem in our book lets us know that a function that can be represented as a power series is both integrable and differentiable on that same radius of convergence. So we know that f of x, f prime of x is going to exist. It's going to be equal to taking the derivative of each one term at a time. So the derivative of the first term, so it's going to be equal to the derivative with respect to x of this whole thing. Right, which means that we have to go term by term by term by term to find the derivative. So that derivative is going to be equal to, okay, well, the first term is some constant, so that's just going to be equal to 0. Plus, now the first term here, remember, we're differentiating with respect to x. With respect to x, this doesn't have any x's in it. This is some sort of an equation based in n, right? So this, for example, this little n, c sub n guy, the c sub n could be something like n factorial over ln, maybe something like that. We worked with those in the previous section. Or it could be 2 to the n divided by n minus 2, right? Some sort of a little equation based in n that will be crunched out and then turns into some constant, some coefficient that goes attached to each one of these terms. So my point being that when we take derivatives, it does with respect to x, then we just treat it as a constant. So this is just some constant, and we take the derivative with respect to x. That means we bring this guy down, and then that turns into a 0. So we end up with c sub 1 x minus a to the power of 0 times the derivative of the inside part, right? We've got to use the chain rule, d dx of x minus a. But luckily that part there is just going to be equal to 1. Okay, so now let's do another one. This is just some constant, c sub 2. Bring down the exponent, that's going to be a 2, times x minus a to the power of 1 times the derivative of d dx of x minus a. And then last one I'll do here, plus c sub 3 times 3 times x minus a to the power of 2 times the derivative with respect to x of the inside part, good old chain rule, minus a. Okay, and then we continue the pattern on in the same process. Dot, 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 dot. Keep going that way. Okay, so let's simplify this a little bit. I'll leave that 0 alone for a second. This first derivative, let's leave the 0 in there. Plus, and now this whole thing turns into 1. This guy, the derivative of, with respect to x, of x minus a, this is just going to be a 1. And then x minus a to the power of 0, that's just going to be a 1. So this first, so the term in front of the c sub 1 is just going to be a 1. So that's just c sub 1. Plus, and then there'll be a c sub 2 times 2. And then this term, x minus a to the power of 1. And then this term equals 1 as well. So this is a 1. And then this is a 1. So all those terms disappear. And we start to see a pattern emerge from here. plus c sub 3 times 3 times x minus a to the power of 2. And then just kind of, even though I didn't write it down, I think we can kind of guess what the next one's going to be. It's c sub 4. And look, there's always a matching number. C sub 2 has a 2, C sub 3 has a 3, so there must be a 4 there. And then the next one is going to be just this x minus a to the power of, and we had 1 there, a 2 there. The guess could be that there's a 3 there. Okay, and then dot, 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 forever. Okay, so then we can express this way. First derivative is going to be equal to the sum of, okay, there's going to be a c. Now, this is just 0, so we can just kind of ignore it. And let's just start coming up with a way that expresses this right in here, starting at 1, 2, 3. So let's make that a c sub n, and let's let this n start at 1. Okay, so starting in 1, going to infinity, that just represents that. Now there's always going to be, there's a number in front, right? So there's sort of this invisible 1 that belongs there, and there's a 1, and there's a 2, then a 3, then a 4, then a 5. So then there's just going to be times an n that goes in there. Okay, and so that takes care of the 2, the 3, and the 4, and we already took care of the c. So then we have this, they all have this power, an x minus a to the power of, and notice the connection between these values. Here we have a little 2, we have a 2, and here we have a 1. 2, 2, 1. And then here we have a 3, here we have a 3, and then we have a 2. So the power is always 1 smaller than these other ones. So here, this should go to the power of n minus 1. So I'm just doing kind of a guessing and checking and confirming that it works out. Let me put it in black and it'll pop out in a weird way. The power of n minus 1. Okay, so here we go. This is that. Notice that I started with 1 now. And when we compare it to the original power series, it seems to make sense from what we know of taking derivatives, right? This is going to be treated as a constant, so we leave it alone. We take the exponent, which is n, we bring it out in front, and then we subtract 1 power from the exponent. And that's exactly what we get here. Right? The only thing that we have to be careful about is that I shifted over and started at n equals to 1 instead of n equals to 0. Anyway, so that's the derivative of a power series. And also, we get to take an integral. So likewise, if we wanted to take the integral of the function f of x dx, which means we want to take the integral of the power series representation of f of x dx. That means we want to take the integral of all of these guys, the integral of, and then we have this expansion as c sub naught plus c sub 1 x minus a to the first power plus c sub 2 x minus a to the second power plus c sub 3 x minus a to the third power plus dot 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 forever dx. And so we know that we can actually integrate one at a time, piece by piece. So it'll be the integral c sub naught dx plus the integral c sub 1 x minus a to the 1 power dx plus the integral c sub 2 x minus a to the second power dx plus integral c sub 3 x minus a to the third power dx plus dot 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 dot. Okay, so then when we integrate each one of these things, we have to raise this by a power of 1 and then divide by that extra exponent, right? That's the pattern we notice. So I'm going to start with this one and then come back to this one. So this one, this is just some constant. It's going to be c sub 1 x minus a to the power of 2, since we raised that up by 1. And then we got to divide it by 2, right? The derivative of this is going to be that. Bring down the 2, it cancels with this 2, subtract 1 from the exponent, we get this. And then the chain rule, which is to multiply times the derivative of the inside part, the chain rule is going to end up giving us a 1 anyway. Right? So in other words, a little check here. Check the derivative with respect to x of c sub 1 x minus a squared over 2. Okay, so the derivative is going to be equal to c sub 1 over 2 times, bring down the exponent, bring that exponent down, times x minus a to the power of 2 minus 1, which is going to be a 1, times, good old chain rule, ddx of x minus a. Luckily, that is going to be equal to 1. And then this cancels with this. And so, indeed, we confirm that the derivative of that is, in fact, c sub 1 x minus a to the power of 1. Right? This is exactly what we wanted. Okay, so I was just confirming that the pattern is working for this guy. So now let's do this one. Now, of course, it's gonna, when you take the integral here, there's gonna be plus some constant, right? I'm already using c's to represent these coefficients of each one of these things, so I'm not sure if I should. So let me put plus some constant with a capital. No, that doesn't look right. Plus some constant. So I'll stick with C because we're just really, really happy to have C. But don't let this C confuse you from here. These are those C's that have a sub-index are the coefficients of the power series. But every book I've ever seen always has just a C to represent the constant that comes when you integrate. Okay, so this integral is going to have its own C. Plus, now this guy, well, that's just going to be c sub 2, and this is going to be equal to x minus a to the power of 3 divided by 3, plus, and then the next one is going to be, plus some c. Well, now this c and this c are not necessarily the same c, but they're all coefficients, right? So it doesn't matter. We can kind of have all these plus a constant all the way out, and then kind of combine them all together. So like, let's say that this is C star and this is C bar, whatever, just two different constants. But then if I bring them together, I can just say let C, let C equal to C star plus C bar. It's just some constant. Okay, so for that reason, we're not going to bother with finding the individual or pointing out the individual constants of each one of these integrals. We're just going to say, well, they all have their own little constant, and then we're going to bring them all together. So at the very end of this, there will be some constant there. Okay, so let me erase this guy, and we'll just not bother with it right now. While we're at it, let me go ahead and erase this. We don't need it anymore. And finish out the pattern. Okay, so we took care of that one. We took care of that one. Plus, this is going to be c sub 3 x minus a to the power of 4 over 4. And now we're ready to figure out what this is. This should be c sub naught x minus a to the power of 1 over 1. If you want to stick to the pattern of all the rest. Right? So it's a pretty easy pattern. In fact, we can very easily guess what the next one is. C sub 4 x minus a to the power of 5 over 5. Right? Plus dot, 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 dot. And like I said, at the end, there'll be some constant, which is really the accumulation of all the individual constants that we got all along the way. We add them all together, and they end up giving you some constant at the end. Awkward to put it at the end, so often you'll see that places put it in the beginning for that reason. It's awkward to put dot, 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 and then plus C at the very end. So very often we might see that C out in front, so just be careful with that. Okay, so we can express this whole thing then using our power series representation. So now we can say that this whole thing is really equal to the sum of, and the pattern is pretty easy. We're back to 0. So we're back to 0, and equals from 0 to infinity. C sub n, that'll take care of that guy. And then we have this power of x minus a. And notice that in every single case, the exponent there and the denominator are the same. 1 over 1, 2 over 2, 3 over 3, 4 over 4. And in every single case, that number is exactly one more unit than the little subindex of the C. 0 and then 1, 1. 1 and then 2, 2. 2 and then 3, 3. 3 and then 4, 4. Okay, so that means that this must have a power of n plus 1 divided by n plus 1, right? And then all of this has a c at the end. So it's the sum of all of these guys. And then when you're done with that entire sum, don't forget that there's this plus c at the end. And because it looks kind of weird that way, very often you'll see that people just kind of flip it around and say it's c plus this whole thing. It goes from 0 to infinity of c sub n, and then it's x minus a to the n plus 1 all over n plus 1. Right? And so this is the integral of f of x dx. If we look at our pattern, power series, remember the power series representation looks like this. Right, so here's our original power series representation. And look what happened here when we took the integral. It kind of followed the same pattern that maybe we'd expect. Right? The pattern is to add 1 to the exponent and then divide by that exponent. Good. And then this thing just kind of stays the same. And notice that we keep the same index value of n starting at 0. And then also we have some constant we might have to deal with. Good, good, good. Okay, so let's look at the actual theorem that's in your book. Okay, so I'm on page 754 of your textbook, and we come to this beautiful theorem right here that describes exactly everything we've been talking about. Puts it in a nice, pretty little box for us. So let's just confirm this is everything we've been looking at. So if a power series, described this way, c sub n x minus a to the power of n has a radius of convergence r greater than 0, then the function f defined by, okay, so this is what we did. We expanded it out this way. This is the expansion of a power series, and then we can consolidate that into this Riemann sum expression, goes out to infinity. Then that function is differentiable and therefore continuous on the interval from a minus r to a plus r, right? Remember, this is a power series function centered at a with a radius of convergence r, where r has to be greater than 0. That means that there exists an interval like this where this is valid, right? So any x value that's inside this interval will give you a true statement, right? You'll get a valid result. Good. And so given that this function is described this way, this is letting us know that the first derivative of the function can be expressed this way, just the way we did it, and so it can be expressed this way as a power series. And the integral of the function can also be expressed this way. Good. The radius of convergence for both the power series, of convergence of the power series in equations 1 and 2, so the power series representation of its derivative and its integral are going to keep the same radius of convergence, capital R. So it'll still be, so if the original function is defined in this interval of convergence, then the integral and the derivative of that function are going to also be valid in the exact same interval, with only one little caveat. The endpoints might be different. So that's the one thing you have to be careful about. You might gain or lose endpoints when you take derivatives or when you take integrals. But the rest of the interval of convergence will stay the same. Okay, so just be careful about endpoints when you integrate or differentiate. Okay, so we can recap those two ideas this way, right? The derivative of our power series is equal to the sum of the derivative of each individual term. That's what this is saying, right? In order to take the derivative of this infinite sum, we can take the sum of individual little derivatives. And same thing with integrals. The integral of this infinite sum is equivalent to the infinite sum of individual little integrals, right? And so that's what this is saying. This has not been proven. The proof of this is incredibly hard and beyond the scope of this class. We're not going to get into it. This is just something we get to use and apply and love and move on with our lives. So don't worry about the proof. The proof is beyond what we're going to look at in this class. But rest assured, somebody did it, right? So somebody went out to show that this is true. And it's true for power series. So keep that in mind. All right, let's work out an example. For example, find the power series representation of f of x equals to ln of 3 minus x. Okay, so find the power series representation of this. Well, remember that the derivative of the ln function will be equal to this. So the derivative with respect to x of ln of 3 minus x is going to be equal to 1 over 3 minus x times the derivative of the inside function here, good old chain rule, times d dx of 3 minus x, which gives you a minus 1. So its derivative is just going to be equal to negative 1 over 3 minus x. Okay, that's looking an awful lot like something we could use. So we want to say that f of x, which is equal to the ln of 3 minus x, is equal to the integral of the derivative of ln of 3 minus x dx. Right, so like this integral is an inverse operation of its derivative. We take a function, we take its derivative, and then we integrate it. We're going to get back to the original function, right? And the reason we want to do that is because now this part in here is going to be equal to that. So that means they're really looking for the integral of negative 1 over 3 minus x dx. Okay, so now that we can manipulate a little bit and say that that's going to be this minus 1. Let's just put that out there. And then I want this to be a 1 here, so I'm going to multiply the numerator and denominator of this fraction by 1/3 over 1/3, right, and sort of distribute it. So 1/3 times 3, it's going to give us that 1 that I want there. It's going to be the integral of, and there'll be a 1 there, minus x over 3 in the denominator. And then there's a 1/3 here, dx, which I can pump out there. And so this is going to be equal to negative 1/3 integral of 1 over 1 minus x over 3 dx. And now that's where this looks like the sum of a geometric. It's starting to look a little familiar. This is the sum of a geometric. The sum of a geometric with a equal to 1, and the common ratio of x over 3. Good. So that's when we say, okay, well then this is going to be negative 1/3 integral of, and then this is going to just be equal to x over 3 to the power of n as n goes from 0 to infinity dx. And so now this guy we want to integrate. And so let's expand this out a little bit. This is saying it's negative 1/3 integral of, and then if we expand this, we end up with x over 3 to the power of 0, that's just going to be 1, plus x over 3 to the power of 1, plus x over 3 to the power of 2, plus x over 3 to the power of 3, plus dot, 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 right, dx. And so we know that we can actually integrate each one at a time. So we'll end up with negative 1/3 times, and then this guy will just be x, plus, and now there's a 1/3, so just pull the 1/3 out here, times, and then x to the second over 2, plus, and there seems to be the 1 over 3 squared doesn't get affected by this, and then we get x to the power of 3 over 3, plus, and then we have a 1 over 3 to the power of 3 times x to the 4th over 4, plus dot, 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 dot. And of course, there's going to be some plus some constant at the end. Okay, well, we can also combine all that together, 1/3 times, and then this is going to be the sum of, and let's look at this pattern. We have powers of 3 to the power of n, so that doesn't change. Looking at this one for n equals to, let me start with n equals to 0, and then I'll come back to make sure that it affects this one, that it does generate this one. But since some of those terms are going to be 1, I'm just focusing on this one. When n equals to 1, I end up with, there's a 1/3 to the power of n there, and that gives me n to the power of 1, 2, 3, and then there'll be 1 over 3 to the power of 0, if you want to continue that pattern there. And then there's an x to the power of, and notice that this is a 1 here, and that's a 2, 2. This is a 2 there, and that's a 3, 3. 3 there, and that's a 4, 4. It's always 1 more. So x to the power of n plus 1 all over n plus 1 out to infinity. And then going back to make sure that it fits for 0, put a 0 there, we just get an x to the power of 1 over 1 times 1 over 3 to the power of 0, which is just going to be 1. And so we could introduce that extra little element here just to show that it fits the pattern. 1 over 3 to the power of 0, 1 to the power of 1, and then it fits the rest of those patterns, but I don't think we need it. Okay, and then there's that plus c there, plus c. So make sure that this whole thing takes care of itself there, and then at the very, very end then there's a c. If I don't put those there, there's the danger that someone might think that there's a plus c for each one of these things. But we want to expand this whole thing out, have a giant infinite sum, and at the end there's a plus c. That's what we want to express. Okay, so we're saying that the original function, zoom out a little bit more, the original function f of x is equal to ln of 3 minus x. And so we're saying that that's equal to the integral of the derivative of that function. These two kind of undo each other, inverse operations. The derivative of this equals this. Good. And then we manipulate it a little bit, make it look like something we could use, and then we can rewrite that into a power series. So now we're saying that that original function is equal to the integral of this power series. And then we were able to expand that and then take the integral of each one individually. We can bring them back together. And so we have our power series representation. We're almost there. So we're bringing it all together. We're saying f of x, which was equal to ln of 3 minus x, this guy, is equal to this. Right? So this function is also f of x equals to this function, minus 1/3, and then I said let's just flip it around so it doesn't look as confusing. C plus, and then this whole infinite sum, 0 to infinity of 1/3 to the n, x to the n plus 1 all over n plus 1. Like that, we're almost done now. What about this c? Can we figure out what that is? If we go back to this expression here, this whole thing equals this, right? So we're saying ln of 3 minus x equals that. Same as this, ln of 3 minus x equals that. So if we focus on this part here, to figure out the value of c, one thing we could do is to replace this value here with a 0. And if we do that, right, if we think about letting x equal 0, then this will be a 0, and then this guy over here will be a 0, and then this guy will be a 0, and then that guy will be, right, all the way down. So all the terms have a 0, so all of these are going to disappear. And the only thing that's going to survive that mess is going to be our constant, and then this negative 1/3 equals this. Okay, so let me write that down. When x equals 0, we'll end up with ln of 3 minus 0 is going to be equal to negative 1/3 times 0 plus 1/3 times 0 to the second over 2 plus 1/3 squared times 0 to the third over 3 plus dot, 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 dot. Continue that pattern forever, and then at the very end there's this plus c at the end there. So we end up getting that ln of 3 equals to negative 1/3 times all of those 0, 0, 0, 0, 0, then there's this constant at the end, so just negative 1/3 times c. So if we multiply both sides by negative 3, we get negative 3 ln of 3 equals to the constant that we're interested in. Right? And then that's the constant that goes right in there. So f of x is equal to negative 1/3 times c, which is equal to negative 3 ln of 3 plus this part, which is the sum as n goes from 0 to infinity of 1/3 to the nth power x to the n plus 1 over n plus 1. And then if we distribute this guy, the negative 1/3 and the negative 3 cancel out to give me my final response, that this is equal to ln of 3 as my constant minus 1/3 times all of this, and goes from 0 to infinity of 1/3 to the nth power x to the n plus 1 all over n plus 1. Okay. Final portion of this, though, is to figure out the radius of convergence. When is all of this valid? Well, all of this is valid as long as, going back up here, the first place where we rewrote our expression. So going back up here, we said that the original function f of x equals to ln of 3 minus x is equal to the integral of the derivative of this. So at this point is when we made this transition where we could replace this with a power series from here to there. And so this is valid on, or as long as x is, this is as long as x over 3 in absolute values is less than 1, which means that the absolute value of x has to be less than 3. So this is for x being a member of the interval between -3 and 3. Right? As long as x is a value in that domain, then this will be valid. And as long as this is valid, then the rest of it is true. So it's kind of a small little window of interval, right? So this is for x being a member of the set between -3 and 3. So this is a perfectly good answer, but we can also manipulate it a little bit, so you might see it in a slightly different form. So that means that our function f of x is equal to this constant, ln of 3, minus, and let's tuck in these two together. So I can bring it into here and rewrite it as the sum as n goes from 0 to infinity of 1 over 3 to the power of n plus 1, and then x to the power of n plus 1 all over n plus 1. And again, this is for x being a member of -3 to 3. Okay, and now since they all have n plus 1, n plus 1, n plus 1, what we could do is do a little substitution here. Let's change this to be f of x equal to, now if we put n equals to 0, 0, then they all start with a 1, right? So if we kind of think about the first terms, this becomes 1 over 3 to the first power, x to the first power, and then we have a 2 here, 1 plus 1, right? That's when n equals to 0. Plus, when n equals to 1, we end up with 1 over 3 to the 1 plus 1, which is going to be a 2. Wait, sorry. This is a 0, and then this becomes 0 plus 1. That's what I meant to do. 0 plus 1. And then this is 3 to the power of 0 plus 1. 0 plus 1. When we have 0, 0, 0, which means really we're starting with 1s. This becomes 1 over 3 to the 1 power, x to the 1 over 1. Okay, when n equals to 1, the next term, plus the next term, then this becomes 3 to the power of 1 plus 1, x to the power of 1 plus 1 over 1 plus 1. So this really becomes 1 over 3 to the second power, x to the second power all over 2. Okay, so what we can do is we can rewrite this using just n, and then changing this little index. Instead of starting at 0, it could start at 1. So now f of x is equal to ln of 3 minus the sum as n goes from 1 to infinity. And now this is going to become 1 over 3 to the n power, x to the n all over n, right? Notice that this, changing the index from n plus 1 to just n for all of them, n plus 1, n plus 1, n plus 1, just changing them to n, and then n, and n. And also changing the place where this starts. This index used to start at 0, so now it starts at 1. This is going to end up giving me the exact same thing. Right? When n equals to 1, we get 1 over 3 to the power of 1, x to the 1 over 1. That's this term. Plus, when n equals to 2, now we end up with 1 over 3 squared x to the second over 2. That's that term. Plus dot, 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 dot. We're going to end up getting the same thing. So because it describes the exact same infinite series, this infinite sum, then this and that are equivalent. It's just a way of simplifying it a little bit. The other way that you can get here, right, just kind of conclude the same thing, is to do a substitution. We can say something like, let w equal to n plus 1. Okay, and so we can just go through and replace each one of these guys with a w. We end up with 1 over 3 to the w times x to the w all over w. Right, just replacing that w. Right, n plus 1 is a w. And now, well, where does it start? Well, when n equals to 0, when n equals 0, then w is equal to 0 plus 1, so w equals to 1. So this is going to be a sum where we let w start at 1. W equals to 1. And then, of course, when w gets infinitely large, when n gets infinitely large, then w is also going to get infinitely large. It's just off by 1. So this still grows to infinity. Good. And now there's nothing special about w. W is just a dummy variable, just as n is. So we can express this back using n's by, again, just replacing the w's. If we change all those w's to n's. Or we can also use k or I or j. These are all popular letters to use to index an infinite sum, a series, or a power series in this case. So we could just go back to our very popular n instead of a w. N starting at 1 to infinity, 3 to the n power, x to the n all over n. Okay, so we have that. And again, this is for x being a member of -3 to 3, right? So this is a power series centered at 0, right? So this is a power series centered at 0 with r, radius of convergence, equal to 3. So r equals to 3. This is the interval of convergence. This guy is called the interval of convergence. And obviously it's centered in the center. Right? It's centered at 0. And we can see that easily here. Okay, so let's tackle something from your homework. Okay, so here are the exercises from chapter 11, section 9. And the one we just finished doing is very, very similar to number 15. So hopefully that'll help you guys figure that out. So let's do one more. How about something like number 18? So find the power series representation for the function and determine the radius of convergence. And we have this guy here. So let's do number 18. Okay, find the power series representation of this guy. It's not going to be easy, not going to be fun. So let's break this up in the following way. I'm going to separate this as x to the power of 3 times 1 over 2 minus x, and then all of this to the power of 3. Right, just kind of separating it out that way. And then I'm going to just take this part inside here and kind of work with that a little bit. So note that if I had 1 over 2 minus x, that's very similar to what I need, except I need to make sure there's a 1 there. So I'm going to multiply the numerator and denominator by 1 over 2. We've done this trick a couple of times now. 1 over 2, 1 over 2. So this is going to be equal to 1/2 divided by 1 minus x over 2, which is equal to 1/2 times 1 over 1 minus x over 2. And now this part here, this looks like our sum of a geometric. The sum of a geometric with common ratio of x over 2. Okay, so then that means that we can rewrite this in the following way. We can rewrite this as 1/2 times the Riemann sum, as this goes from 0 to infinity, of this thing, the x over 2 raised to the power of n. And this is going to be valid as long as this is 4, or as long as absolute value of x over 2 is less than 1, which means that the absolute value of x must be less than 2. So therefore, x must be a member of the set between -2 and 2. So as long as that's respected, then this will be true and valid. Okay, so now I'm going to get rid of the middle 2 here and just say that that must mean that the original one is equal to that, right? So we have that 1 over 2 minus x is in fact equal to this, which is equal to 1/2 sum as n goes from 0 to infinity of 1/2 times x to the nth power over 2 to the nth power. And so I can combine these guys. Oops, I already put it in there. So I'm just bringing in this 1/2 inside here, and that's what that guy is. And so this can be simplified even more and say that 1 over 2 minus x is in fact equal to the sum of x to the nth power over 2 to the n plus 1, as n goes from 0 to infinity. And just to kind of expand this just a little bit and have a couple of terms to play with, when n equals to 0, we end up with a 0 there, and then a 1 here, so we'll just end up with 0. 0 there, we end up with x to the blank to the plus 1. So there's the 0 power to the 0 power. The 0 power is going to be 1, so this is going to end up being 1 over 2. X to the x to the 2 to the, and then when n equals to 1, that'll be a 1 there and a 1 there, plus last one, x to the, and then it'll be 2 to the power of blank plus 1. So this time this will be a 2 there and a 2 there. And then we keep going that way, right? Plus dot, 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 that way. Okay, so this is then equal to 1 over 2 plus 1 over 2 squared x plus 1 over 2 to the third x squared plus dot, 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 like that. Okay, what we want to do now is take the derivative of both of these two, right? The derivative of both sides, the derivative with respect to x of 1 over 2 minus x, and then that is going to be equivalent to the derivative of this side. The derivative with respect to x of this guy, from 0 to infinity, of x to the n over 2 to the n plus 1, which means it's really the derivative with respect to x of this whole thing. 1/2 plus 1 over 2 to the second x plus 1 over 2 to the third x to the second plus dot, 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 dot. Okay, well, this one's not too hard. The derivative of this is going to be equal to, think of this, d dx of 2 minus x to the power of -1. That's equivalent to there. So the rule is to bring the exponent out in front. So that'll be a -1 times 2 minus x to the power of, subtract 1 from the exponent, that's going to be a -2, times the derivative of the inside part, times the derivative with respect to x of the inside part, which is a 2 minus x. That's going to give us a -1. But then this -1 and that -1 cancel out. So this whole thing is just going to become this to the power of 2. So this whole left side, when I take the derivative of this, is just going to become a 1 over 2 minus x squared. Okay, that's what this side is. And then this side, let's skip that one in the middle for a second and then just jump over to this side. Well, okay, so it's gonna, in the middle, it's gonna have some sort of Riemann, and it's gonna be some sort of a fraction. We'll figure it out in a second. Here, on a term-by-term basis, we'll end up with a 0 plus, and then that first term is gonna become 2 to the power of 1 over 2 to the power of 2. X becomes a constant. Plus, and then we'll end up with 1 over 2 to the power of 3 times 2x to the power of 1, right? Plus, okay, well, if it had one more term, let's zoom out a little bit, and then, you know what, I should have had one more term here to really make this pattern pop out. So let's come back up here and add one more term. So if we continue with this pattern here, the next term would be 1 over 2 to the power of 4, x to the third power, right? Since these powers were going 1, 2, 3, and then in the denominator we had 2 to the first, 2 to the second, 2 to the third, 2 to the fourth, plus dot, dot, dot. Okay, and so now this one is going to be 1 over 2 to the fourth power, 3 times x to the second power, plus dot, 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 and so on and so forth. Okay, so now to get the middle one here, let's go back and look at our formula and make sure we're following that pattern right here. And so if we wanted, if we had a function that was a power series, expressed as a power series, then look at the pattern. It's just going to be kind of take the derivative with respect to x. So based on that, hopefully, maybe do like a little guess and check and confirm that it matches what we expect. So we're going to leave this alone. This is going to still have the 2 to the n plus 1. And then we take the derivative of this. Remember, the pattern is to bring the n out in front. So it'd be an n times x to the n minus 1. And we also change this by going up by 1, right? And that's because that first term was 0, so we don't need to start at 0 anymore. And let's just confirm that it matches the rest of these. When n equals to 1, we'll end up with 1 times x to the 1 minus 1, which is 0. So that'll just give us a 1 there. And then 2 to the 1 plus 1 gives us 2. Okay, so that matches this one when n equals to 1. N equals to 1, we end up with 1 times x to the 1 minus 1 all over 2 to the 1 plus 1. This is all going to be 1, and this is just 2 to the second power, so that gives us this one. When n equals to 2, we'll end up with 2 times x to the 2 minus 1 all over 2 to the 2 plus 1. That's going to be 2 to the third power, that's this guy. 2, that's that one. And x to the power of 2 minus 1, that's that one. Okay, so it kind of confirms that this is going to be equal to that. Okay, so we have the first derivative, and it looks a little closer to what I'm looking for. But if you're wondering why we took the derivative, well, it's because, coming back up here to what I'm trying to do, I'm looking for something that looks like this, 1 over 2 minus x to the power of 3. And I started with just this inside part, and I just managed to get it to the power of 2. So if I do it one more time, I'll get it to go to the power of 3. So let's do that one more time. Right, so we've established that this is true. So now let's take another derivative. The derivative with respect to x of this term now, 1 over 2 minus x to the power of 2. And we also want to take the derivative of this, the derivative with respect to x of the power series starting at 1 to infinity of n x to the n minus 1 all over 2 to the n plus 1, which is also equal to the derivative with respect to x of this side, 0 plus 1 over 2 to the second plus 1 over 2 to the third, 2x to the first power plus 1 over 2 to the fourth times 3x to the second power plus dot, 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 dot. Keep going in that pattern, right? Okay, so now the derivative of this one is pretty easy. Let's just rewrite it this way. It might make a little more sense if we think of it as 2 minus x to the power of negative 2. Right? We know that that means we bring down the negative 2, minus 2, times 2 minus x to the power of minus 3, times the derivative of the inside part, which gives you this 2 minus x, good old chain rule. And so now this guy becomes a negative 1. This negative 1 and this negative cancel to give you a positive 2. And so this first derivative over here turns out to just be 2 over 2 minus x to the power of positive 3, right? From a minus 3, we turn it to a positive 3 because it goes underneath the fraction into the denominator. Okay, so that's this derivative here. Let's skip the 1 in the middle. That's going to be equal to some, right? We'll come back and look at our pattern one more time. But let's just skip that for now and go over here to this last one. So whatever that is, it's got to be equal to, so now the derivative of the first, well, the derivative of 0 is just 0. So that'll just give me a 0. Plus, the derivative of this constant, well, that's just going to give me a 0 again. Plus, the derivative of this guy, well, we just bring down the 1 out in front, the power of 0. So this one's going to be equal to plus 1 over 2 to the third power times a 2 times a 1. And just for the sake of this pattern, I'll just put to the x to the 0 power, which of course that's just equal to 1. Okay, plus, let's look at the next one. There's this 1 over 2 to the fourth power times a 3 times a 2 times an x to the 1 power, right? And again, I should have added one more term into this guy just to make sure that the pattern carries down. So let's come back up here and then insert one more value into this little sequence. So this is going to be plus 1 over 2 to the power of 5. And then looking at this pattern, this is a 2, then a 3, this is going to be a 4, x to the power of 3. And just to be clear, how about one more? 1 over 2 to the power of 6 times 5 times x to the power of 4 plus dot, 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 right? So just kind of expanding that a little bit longer. Okay, and so now this derivative was this one. And so now this derivative here is going to be plus 1 over 2 to the power of 5. And there's a 4 times a 3 times an x to the second power plus 1 over 2 to the sixth power times 5 times 4 times x to the third power plus dot, 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 dot. Keep going that way. I guess I don't need the bracket. keep going that way, right? So that's the derivatives. Okay, so now we want to write down the Riemann sum expression of all those derivatives. Okay, so now look at the pattern that we had before. We had our original, here's our original Riemann sum, and from here we were able to go to here, or to here, and look at the pattern. The part of this that has the power of 2 to the n plus 1 didn't change at all, right? Because the derivative with respect to x, it doesn't affect the 2 to the n plus 1. It does affect the x to the n, and then we just took the derivative of that like normal. So let's do that again here. This is going to be something that the 2 to the n plus 1 does not get affected by. And then we're going to have an n, and then we're going to have an n minus 1. We're going to bring this down, and then subtract 1 to the exponent. So this will be n times n minus 1 times x to the power of n minus 2. Good. And now we just got to make sure that this thing matches. The first one that happens is when we have a 3 in the exponent. So it would make sense that we change this up and move it up to 2. Right? You see that when n equals to 2, when n equals to 2, putting a 2 everywhere, I'll end up with 2 times 2 minus 1 times x to the 2 minus 2 all over 2 to the 2 plus 1. And all of this gives me exactly this term. So all of this gives me that term right there. Right? It simplifies to give me that one. And then when n equals to 3, we end up with 3 minus 1 to the power of x 3 minus 2 all over 2 to the power of 3 plus 1. So this is when n equals to 3. And this, all of this, gives me that term, right? X to the power of 3 minus 2, that's going to be x to the power of 1. 2 minus 1 is a 3 minus 1 is a 2, and then we have that 3, and then 2 to the power of 4. So that's that term right there. Finally, last one I'll do, n equals to 4 means we'll end up with 4, right? And I'm following this little pattern over here when I create this. 4, and then 4 minus 1 times x to the 4 minus 2 all over 2 to the 4 plus 1, right? And so all of this gives you exactly that term. 1 over 2 to the 5th power, 2 to the 5th power. There's a 4 and there's a 3. There's a 4 and a 3. And then x to the power of 2. And that's this guy over here. Okay, so this is exactly the power series that describes all of that. All right, so let's glue it all together. What do we have? We were able to establish that this is equal to this. So let's go back to our original question. Bringing it back to the original question, it was this. F of x equals to x over 2 minus x to the power of 3. And we were trying to find a power series representation of this. So this was the original question. Okay, so then we're going to separate this a little bit and say that this is equivalent to x to the 3rd power times 1 over 2 minus x to the power of 3. Okay. And so now we can introduce an extra 2 in here and say that this is x to the 3rd power all over 2 times 2 over 2 minus x to the 3rd power. Right? These two kind of undo each other. And now we've established that this is exactly this, and it equals to exactly this. So now we can say that this is equivalent to x to the 3rd power over 2 times this series, starting at 2 to infinity, of n times n minus 1 x to the n minus 2 all over 2 to the power of n plus 1. Good. Okay, so now we can introduce this in here and simplify things just a little bit. This guy, we're going to bring this inside here now and say that this is the sum as n goes from 2 to infinity of n minus 1 x to the third power times x to the n minus 2 all over 2 to the first power times 2 to the n plus 1. And then I'm going to combine those and say that this is equal to n times n minus 1 times x to the power of n minus 2 plus 3 gives you a plus 1 all over 2 to the n plus 2 power. Okay, so this guy we can simplify a little bit more by let's rewrite this so that we start off with a 0. This is a perfectly good answer, but I think you'll find a lot of solution manuals prefer to start with a 0 instead of starting with a 2. So why don't we come up with a good W substitution that will result in having a 0 here. So if we put in a 2 into there, the first term is a 3. Right? To kind of if we start to expand this out a little bit, when n equals to 2, what do we end up with? When n equals to 2, we end up with 2 times 1 times x to the third power all over 2 to the fifth power. I'm sorry, fourth power. Right? Replacing that with a 2, replacing that with a 2, replacing that with a 2. So that's the first term. When n equals to 3, the next term, n equals to 3, plus, we end up with a 3 times a 2, 3 and a 2, and then x to the power of 4, all over 2 to the power of 5. Okay, so if I want to start off at 0, this is 0, and I want that to be a 3, it would make sense that it would be the variable plus 3, so that when the variable is 0, we get that first value equal to 3. So maybe a bit of a guessing and checking. Let's let this new variable w, so let's let w equal to n minus 2. That way, when n is equal to 2, w equals to 0, and then that's how I know I can start my sum at starting at 0. So if I want to do that, then what I want to do is move this over. So w equals to n minus 2 must mean that w plus 2 equals to n. So I'm just going to come up here and replace all those n values with w plus 2. And so I'll end up with sum, and then I'll come back and insert those in there. So this will be a w plus 2 for that first n, and then it's a w plus 2 minus 1, and then it'll be times x to the power of, and then w plus 2 plus 1 divided by 2 to the power of w plus 2 plus 2. Right? So I went through, and every place where we see an n, I replaced it with a w plus 2. Right? W plus 2, W plus 2. 1, 2, 3, 4 places. So 1, 2, 3, 4 places. I replaced the n with a w plus 2. And then the whole goal was to start at 0. So when, over here, this is when n equals to 2, that one right there, that means that w equals to 2 minus 2, which means w starts off at 0. That was our whole goal. So w will start off at 0. And then when n is infinitely large, right, infinitely large number minus 2 is still infinitely large, so that still goes up to infinity. So I managed to change the index down to something that starts off at 0. And now we just simplify that a little bit as best we can. And so that will be the power series, starts off at 0 to infinity, of w plus 2 times w plus 2 minus 1 is going to be w plus 1, x to the power of w plus 3, all over 2 to the power of w plus 4. Okay, well, there's nothing special about the letter w. It's just a dummy variable. And oops, look at this. I'm so used to using n. I wrote n there. This is for w going from 0 to infinity, and then we have it written in w. But there's nothing special about w. We can just write it into, based in any variable. So why not go back to our good old faithful, friendly neighborhood n value, right? So, or we can say that it's equal to sum as n goes from 0 to infinity of n plus 2, n plus 1, x to the n plus 3, all over 2 to the n plus 4. Okay, so there, we found it. Kind of bringing this back up to the very top. Remember our original goal. It's gonna bring this up is a big problem. Our original goal was to figure out a power series representation of this. So we separated it like this, and then once we have it in this form, I had done some previous work to show that this is this representation. So we can glue them together with this multiplication, and then I was able to bring this on the inside, and then simplified and combined things and change the index and all that. But the original function we're working with is equal to all of this. That's what we just found. So bringing that all the way down to here, we're saying that the original function f of x, which was equal to x over 2 minus x, 2 minus x raised to the power of 3, is in fact equal to this power series representation. And this is valid as long as, and then coming back up here, we wrote down that this was only valid. Come back up here, we saw that when we made this change right here, and we noticed, oh, this is the sum of a geometric, that this is true as long as the x over 2 in absolute values is within 1. Right? That just goes back to the common ratio in a geometric, which means that x is a member of the set between -2 and 2. So that's what this is good for. As long as this is true for x being a member of the set between -2 and 2, which means that this is a power series centered at 0. This is a power series centered at 0 with a radius of convergence equal to 2. Okay, that should be enough for you guys to work on your homework. As usual, let me know if you have trouble with anything. I'll be available for Zoom meetings if you need anything. So let me know how you're doing.